In this video, I want to investigate whether I can make this particular piecewise function continuous everywhere. Well, I have a little bit of freedom. Notice that there's a c inside of there, so the hope is that by manipulating the c, I can make it continuous everywhere. First, I want to note this. If I look at this function here or this function individually, like if this applied for all values of x, either of those are just polynomials. One's a quadratic, one's a linear. And polynomials are continuous absolutely everywhere. There's no division by zero, there's no infinite spikes, there's no oscillatory behavior. These are continuous everywhere. So the only possibility, the only spot where there could be a problem was this value of x equal to 1. That's where it might be that the limit from the left and the limit from the right and the function value might be different. Okay, so let's match them. Our goal is this. I want to say that the limit as x goes to the interesting spot, the 1, as x goes to 1 from, let's do the left first, of f of x. What I'm hoping is that this is going to be the same thing as the limit as x goes to 1 now from the right of my function f of x. So I need that to be the case if I have any hope for it to be continuous. And indeed, my third condition is that I want it to be equal to f of 1. That one's going to come more or less for free. Okay, well now let's do the one from the left. Now, from the left is this top one up here, x values less than 1. So, in other words, this is the same thing as the limit as x goes to 1 from the left of c x squared plus 1. And this one over here is just going to be equal to the limit as x goes to 1 now from the right of 2x minus c. And the f of 1 is just going to be plugging in here. This is going to be equal to 2 minus c. So these are the three different things that I need to be equal. Okay, well, how do I do these limits? Both of these limits over here are easy in the sense that these are polynomials, so they're continuous. So to compute a limit, I just plug it in. So in this case, if I plug in 1 for the value of x, so this is equal to 2 minus c, the same value as the function value as we would have expected. And then over here, I'm going to plug in 1 and I'm going to get c plus 1. So this gives me an equation. It tells me that I want c plus 1 to equal 2 minus c. So let's do that. We're going to have c plus 1 to be equal to 2 minus c. And then if I do a little bit of manipulation on this, okay, I'm going to move this c over and this 1 I'm going to subtract off. So I'm going to have a 2c is equal to 1. And so finally I have c equal to the value of 1/2. And indeed, when I do this, this value of c equal to 1/2, it fixes the potential discontinuity at 1. The limit from the left is equal to the limit from the right. So yes, indeed, this is continuous at 1. And because it's continuous everywhere else, as they're polynomials, it's continuous everywhere.